these are actually two they're very related, but separate things that are both really of interest to me because I have been watching meteors streak across the sky for most of my life, and it's a part of my hobby for me. And I actually work in helping in research on meteorites as my one of my volunteer daytime jobs now. So I'm going to divide this into three sections and start out just talking about our planet running into things. You can all see my screen okay? I hope I'm sharing this right. That come through?
Yep.
Looks fine. Looks
Okay.
fine.
All right, good. Can you see my mouse going around so I can use it as a
Yes.
pointer? Good. That's what I'm trying to do here. All right. So our planet running into things. When we think of the solar system, right off the top of our heads, most people would think, well, there's the sun and there's planets going around it. And if you live in Flagstaff, I have to add Pluto back into the picture. So officially one of the planets there. But there's really a lot more to our solar system than the sun and the large planets we see. For example, this is a graphic developed from data from, there's a pair of satellites out there. They're actually going around the sun in Earth's orbit. They look at the space between our sun and our planet to see the Earth-Sun interactions. And one of the things they also see is that there's all this dust and debris, even in our inner solar system, going around in the orbits of the planets. This again is an artist depiction. This is not to scale or anything, but this is showing where these heavy bands of dust and small particles and bits and pieces are. It's cleared around the planets because they've sucked it up there, but we can also go out farther and see across our solar system the remains of the formation of our solar system, basically. So this is a artist impression of a protostar here forming, and this disk of accretion material spinning around it, and out of that are condensing planetesimals and planets. But what happens in the end is some of this debris is left over that doesn't get sucked up into the star or by the planets. We see this dust in our solar system. If you live in it or go to a nice dark place, especially in the springtime in the evening or in the fall in the morning sky, this triangular wedge of light streaking up the sky after sunset is the zodiacal light, and that's actually sunlight reflecting off of this dust out in the solar system. So there's all this fine material still floating around from leftover from the formation of our solar system, and then there's all these pieces. This is looking down on our solar system, and the schematic with the sun in the center and Mercury and Venus and Earth and Mars in this inner area, and then all these asteroids. There's 18,000 dots on this map showing asteroids. You can go to the big heavy asteroid belt between Mars and Jupiter, and then even out beyond Jupiter and Saturn and Uranus, there's even more still asteroids circling around our sun. So there's a lot of smaller things out there besides the big planets going around the sun. Let's see if I can get a little movie to play for you here. This is courtesy NASA JPL plotting, as it's saying across the bottom, discovering more and more near-Earth asteroids by 2009 here, and then by 2018, and then they're going to drop in all of the other asteroids that were known come 2018. So this is almost 20,000 little dots going around. These are all asteroids that are circling our sun. So again, smaller bodies than planets, but a lot of stuff out there. So what happens with the dust and the other debris and even the asteroids is all that material is orbiting the sun, just like the planets are. But occasionally things run into each other, or they come close to each other, or they're disturbed by a planet, and they can fall in closer to the sun. If we take that asteroid belt in the lower left of this illustration, and zoom out from it and get beyond all the planets here. This is Pluto and its orbit here, and Uranus and Neptune out the edges of theirs. We get to this next belt of frozen things out there, frozen bodies. These are everything from little ice balls to comets to dwarf planets that are out there in this frozen zone called the Kuiper Belt. We can zoom out a lot farther yet to where that comes, this little dot in the center of this huge cloud called the Oort cloud, which is basically made up of cometary-like bodies, frozen ice mostly, but ice and dirt and other materials. So some of the comets that come into our inner solar system actually end up coming from all the way out there in this Oort cloud. So there's a lot of stuff going around the sun. And how the Earth runs into them is, well, again, these things, if they fall out of their nice stable orbits, wherever they're out or going around the sun, things will tend to drop in toward the sun if they get disturbed. And the Earth is running into this material, both the leftover things from the formation of the solar system and these other things that are falling in. So I put dust here as the first thing to talk about. Again, I showed that picture of the zodiacal light. That's basically dust out there. In reality, this stuff is raining down on Earth all the time. We sweep it up as the Earth travels along in its orbit, just being drawn in by gravity and the Earth running into it. And these really fine particles, dust size, again, like flour, like smaller than sand, like silt, and they don't tend to burn up in the atmosphere. They have such a large surface area compared to their mass, they'll just slow down as they encounter the Earth, the drag of the Earth's atmosphere, and it ends up drifting down to the surface of the Earth. And along the way, some of these almost microscopic bits will have water condense on them, and they'll become ice crystals to either then go on to becoming raindrops or snowflakes or whatever. So some of the cloud formation is due to dust falling in the atmosphere. If we look at how much we're getting, somewhere between, and this is a hard figure to figure out, so I put a whole wide range in here, between 500 to 300 metric tons per day of material is swept up by the Earth. And that includes meteorites that fall, but they're actually a very small percentage of that mass. Let's see if I can get my slide to go forward. There we go. Because most of that tonnage is just this dust drifting down. So we've got these very fine dust particles. If we go up, another notch in size, we get into the meteoroids and the asteroids. So these are solid things made out of something like rock or metal. And just as a matter of definition, a thing out there floating around the solar system that's not a planet, if it's larger than a meter, or a subplanet, I should call, if it's larger than a meter, we call it an asteroid. If it's between a meter and down to around 2 millimeters, then we call it a meteoroid. If it's less than 2 millimeters, it just falls into that dust class. This is not the old definition. Actually, when I was a kid, the books would say that a meteoroid is the same thing as an asteroid, but we can't see a meteoroid looking out into space. The things we look out and see with our telescopes are asteroids. Well, technology keeps on changing, so we keep on seeing smaller and smaller and more things. So this has become more the standard definition, that it's this meter range. If it's below a meter in diameter, it's a meteoroid instead of an asteroid. So meteoroids are what make meteors and what makes shooting stars for us. When you go out at night, you see that streak of light, it'll flash across the sky. Whether it's a faint little quick one or a longer one that's brighter, those are things in the meteoroid size range that the Earth is running into. If you get this little bit of debris that's bigger than, say, about a centimeter across, you'll have a really bright meteor, something the size of a marble or the size of a jawbreaker, or heavens, the size of a golf ball would make a really bright streak across the sky. You get what you call a fireball or a boloid. You might see it break up at the end of its flight into pieces. But the ones that appear as a single streak of light and are more like the brightness of a star are just regular meteors being caused by generally a meteoroid that's the size more of the grain of sand. If you get up to the size of a meter across, you might actually have something reach down to the ground then and not gets destroyed in the atmosphere. So something closer to meter or above, that's the range where you're going to get meteorites from. But again, most shooting stars that we see are about the size of a grain of sand. Again, reviewing the definition there, a meteoroid is a rock out in space. A meteor is the light we see in the sky. And a meteorite is what makes it to Earth's surface if something does. So, now we get bigger than meteoroids. We're into the range of asteroids and comets. And Earth runs into those. Fortunately, not really often. The last one that people noted, besides the people who monitor for atomic blasts, who see things go off over the ocean that nobody else notices. The one big one that made the news was almost 10 years ago now over Chelyabinsk in Russia, that became brighter than the sun as it streaked across the sky and created sonic booms that were big enough to shatter windows in buildings. And then at the end of its flight, ended up showering thousands of little bits of rocks down on Russia. You can go back to Siberia in 1908 and the Tunguska event that leveled about 2,000 square kilometers of forest, but with a explosion bigger than anything like we've ever done with H-bombs or anything. That was an asteroid coming in. Or you can go back 66 million years ago to the asteroid that hit that probably contributed to the extinction of the dinosaurs and the mass extinction at that time. So this is large things hitting our planet. I'm going to switch from the running into things to talk about shooting stars specifically for a little bit more. Again, looking at the mechanics of them. So we've got Earth in its orbit here. We've got the sun way off the screen to the left here. Earth is traveling along in its almost circular orbit at about 67,000 miles an hour. It's going really fast. So it's roaring through space around sun at that speed. It's also spinning around its axis, giving us day and night during that time. So while it's sweeping through space like this, if it hits something with that much speed, you're going to have some effect of this really large impact. You also have the effect that other things that it's running into are also orbiting the sun, and their orbits may be going in different directions. So you actually may have them going almost in the same direction, so the one speed is subtracted from the other, or you may have them going in opposite directions where the speeds total up together and make an even stronger, a more energetic impact. So you can have things like this by running into stuff at that sort of speed, where a metal asteroid hit the atmosphere and plowed right through it and then hit the ground with so much energy that this is, of course, Meteor Crater just off to the east of you there, and the folks who were in Flagstaff. It's so much energy that it atomized the asteroid itself pretty much, and a lot of the rock that it hit, and it blew this massive kilometer-wide crater into the ground. So this is the entire energy of this came from the motion of those two bodies, the speed of the Earth plowing through space and the speed of that asteroid, whichever direction it was coming from when it hit. Come on, let's go forward here. There we go. So to me, the interesting thing about meteors, the shooting stars we see, is where they really happen. You've got, again, this immense energy of the Earth traveling at that incredible speed. Well, Earth's atmosphere is really very thin. Here we are looking from the International Space Station, and we've seen the sunrise over there, but you can see, compared to the diameter of Earth here, how very thin the atmosphere that you can see here is. If we look at this in a schematic, um, the atmosphere, of course, gets thinner the farther we get away from Earth's surface. And the part of the atmosphere that we really think about is this area called the troposphere here. And it goes, just barely higher than Mount Everest here. Airplanes fly at the top of that. Most of the clouds we see are in that range. The only place we can breathe and living things really live are in that area, which is relatively small percentage of the total measurable atmosphere of Earth. Meteors don't streak through the sky down here. They're way up, not in the stratosphere, all the way up here in the mesosphere. These are meteors being illustrated in the picture here. The air is incredibly thin up there. It's a very small fraction of the density that it is down here. But again, the speed of these impacts, partially because of the speed of Earth running into the things, is so intense that these little bits of material can't make it down that far. Again, to become a meteorite and actually hit Earth down here, you have to have a large enough mass up here that burning away and melting it all, it can still serve, and all of the forces that play upon that sort of impact, it can still survive that and make it down to the ground. So when we go out and see shooting stars, we're looking way up here. We're looking 40 miles high. We're looking 50 miles high, where those little streaks of light are happening. And we know that because we can triangulate on them. We can take pictures of them from two places and see the angles that they are up in the sky, and just use our trigonometry to say we know exactly where this occurred. So I mean, again, to me, this is very interesting. We're seeing these brief flashes of light from sand-sized bits of debris hitting Earth way up there in the atmosphere. I guess I should say too, if somebody has a question, I should pause more often. I'm not sure if I can see when I'm sharing screen, if I can see if someone raises their hand. But feel free to butt in if you have a question, because otherwise I just tend to roar along. Talking about, again, about this mechanic of hitting the atmosphere, those of us who are old enough to remember sending people to the moon, remember the re-entry of the Apollo capsules, or before that. Well, the Apollo capsules were actually going faster than the Gemini or the Mercury capsules were. So you have an Apollo capsule that's going, that was going over 24,000 miles an hour when it first entered the upper reaches of Earth's atmosphere. But again, consider about how much faster this is that the Earth is going around the sun. So this speed, with this intense heat that was generated on the capsule, they had to have the heat shield on it that ablated away to absorb and to create friction to slow down the speed of the spacecraft. That was a relatively low speed compared to the actual speed we have here with the Earth moving around in its orbit. Looking at a meteor itself, so this is the streak of light of a shooting star from the Perseid meteor shower in 2017. I took this picture. With our modern digital cameras, we see things beyond what the human eye can pick up. And in this case, oftentimes, when I first saw this in digital pictures, I was trying to figure out why there was always this coloration on, I'm hoping you can see it on your screens, but on images of meteors. And then I started capturing them myself and seeing it. So the meteor trail tends to be a greenish color and then turn into a pinkish color. And you can still find plenty of books and websites that will tell you, I'm sure if you Googled it, which I haven't lately, they will tell you that this color is caused by the material in the meteor. So say, oh, there must be copper in it or barium in it or something or other that's making this green color. That's actually incorrect. For these sand-sized particles, these shooting star-sized particles that we're really seeing most commonly, this light is not being given off by that little bit of sand burning. This light is actually the atmosphere glowing. This particle is hitting at maybe 80,000 miles an hour, hitting this upper atmosphere here, and it's actually tearing the molecules apart. So what the colors are here, the green and the pink are molecules in our atmosphere glowing because they're being ionized by being shredded by this little bit of sand hitting them so hard. So we have oxygen giving off its triply ionized glow of green up here at around 95 kilometers in altitude. And then down a little bit lower, it switches to this more pinkish glow of this hydroxyl molecule, again, being ionized by being ravaged by that little particle roaring through it. So we're not actually seeing this little bit of rock or metal heating up and glowing and showing its spectrum until we get to the point of the really bright meteors, like I called fireballs, where you're having something that's the size of a golf ball or the size of a baseball coming in, and that material is actually burning off. And then you can start to take spectra of those and see the iron in them and see the other, you can see the silicates in them, you can see the other atoms and molecules within the meteorite itself. So this little white flash, this appears to white to the eye because our eyes are seeing these in our night vision, which is just black and white. But that little white flash, again, is actually the atmosphere glowing and not the little bit of sand glowing. So yeah, again, normal shooting stars, especially fast ones. This atmospheric plasma glowing. So what about meteor showers? What makes a meteor shower? And what's the relationship to comets? Well, there are certain times of the year, if you go out for a certain week in August or a certain week in December or a certain week in January, you might see a lot of meteors on a given night. And that's called a meteor shower. It happens at the same time every year. And they're related to comets. And how that works is comets are balls of ice and dirt, basically. Ice and that dust that I mentioned is still floating around the solar system, and sand-sized particles and little bits of stuff like that. Not big rocks, not boulders, not house-sized things, not mountain-sized things. That's all ice, but in the ice there's a lot of this dirt. And as the comets come in their orbit close to the sun, they start to sublimate off, they start to melt off, and the water in them blows off and the other gases in them blow off, and it takes some of this dust along with them. So here we have Halley's Comet. We have a lot of comets that are periodic, like Halley's is. It's this green oval here, or ellipse, I should say, that keeps on going around in its same path. Every 76 years, it comes back around again. So it has its orbit, just like Earth has its orbit in here. There's Earth, and or Jupiter or Saturn. And it just does that regularly. There's other comets that come in very rarely. I saw Hyakutake, that was, gosh, what year was that? It was in the 90s. But yeah, its orbit, it's going to come back in 17,000 years. You have other ones that stay in a close orbit, but these orbits can cross Earth's orbit, and if it's a periodic comet, it can leave material behind. So what happens is, let's see if we can get to another picture. Here's an actual nucleus of a comet taken by a spacecraft that went out to get close to it and look at it. It doesn't look like a nice, neat ball. It looks like an apple core, sort of. It's being ravaged by the sunlight hitting it. The ice is melting and sublimating away, and it's blowing off into the vacuum of space, and it's carrying dust and particles along with it. If that comet is in this periodic orbit, it'll be returning on that same path again all the time. This illustration shows the tail formation as it gets close to the sun. Enough material is sublimating off that it starts blowing away. You get two tails that form. Come on, picture. There we go. Here's Comet West. Here's two tails on it. This blue is an ion tail, which the solar wind blows straight back away from the sun. So it's always a straight line facing away from the sun. The dust tail, which is what the yellower tail is again dust-sized particles. And that gets carried away by sunlight, actually, not the solar wind, but by just the pressure of sunlight blows it away. So it tends to drift. This comet is moving this direction toward the left, and in its orbit, again, the ion tail will always face directly away from the sun, but the dust tail will drift behind as the nucleus moves off the left of the picture here. So you get these two tails, but what we're more interested in is the fact that, as this little caption says here, larger particles, that is larger than dust, when you get to the, say, sand-sized particles or the gumball-sized particles, they are not affected by sunlight or the solar wind. They just drift into the orbit of the comet. There's nothing really taking them away from the nucleus otherwise. So what happens is this orbit, this whole path here, tends to, over time, to fill up with comet debris. So you have this loop, every little bit of sand in here, or every little something the size of a raisin or whatever in here, is drifting along in that same orbit where the parent comet nucleus is still going around. So it'll keep on orbiting the sun in that area. And what we're interested in is where this orbit happens to cross Earth's orbit. We have, again, here's Earth in its orbit, and it's heading along at that incredible speed. And it comes up to where there's a comet's orbit that is in the same plane as it. The one thing I want to point out, besides the not to scale part, this isn't a comet's orbit isn't a two-dimensional thing like a chalk line on this drawing here. It's actually going to be more like a tube. It's going to be more like a subway tunnel or whatever. So this is looking at a cross section of it. You're not looking through a flat little line you're going through here. It's a whole three-dimensional thing, the space of this orbit with all this stuff floating along it, all going along in whichever direction the comet was going here. It'll be orbiting in the same direction. So when Earth passes through this, it's going to smash into the stuff in the comet's orbit.
Question.
Go ahead.
So these things are in orbit. So what's causing these larger than dust particles to stream off of the body and then reach the orbit?
Oh, very good question. So the body, the vast majority of the mass of a comet is volatile material. It's frozen water. There's also other frozen gases in there. But when it gets close enough to the sun, just the sunlight on it will cause that to melt away or actually sublimate away. It goes right from being solid to being, gas and thrown off. So there's nothing holding together. It's like if you had concrete with pebbles in it and you suddenly took away all of the cement itself and left the pebbles just there wouldn't be anything holding it together. So they drift off of the nucleus of the body of the comet because there's no glue left. So there's as the surface of the comet wears away, basically the gas and water will blow off into space, and it just leaves this other material hanging there, basically. So some of it ends up going a little slower, and some might end up going a little faster than the nucleus of the comet is itself. So it spreads out around the comet. Does that make sense? I guess if I answered the question, if that helped.
Yes, sorry.
Okay.
Drew, I have a quick question.
Sure.
Does a comet have a life?
Yes, definitely. We've seen comets that, in theory, like Halley's Comet, we don't know for sure when it started in the orbit that it's in. Things can change. Orbits can get disturbed. So you can have something that wasn't, you can have a comet that wasn't in a orbit bringing it in by the sun, and something disturbs it out there and knocks it into an orbit where it falls into the sun, and then it becomes a regular orbit. So we don't know how long it's been coming around, but we've watched comets fade away, basically. We've watched a lot of comets run into the sun. So that's become a regular thing we've had spacecraft that watch the solar atmosphere for decades now. And one of the things they almost regularly see, the ones that watch the corona of the sun, they see comets falling into the sun. It's just that the comet's orbit took it a little too close and it got too hot. And we'll see them like go around the backside of the sun and not come back out again because they just fell apart from, but we've certainly seen them getting smaller. So yeah, theoretically, anything that's outgassing and losing mass every time it goes past the sun is going to have a finite lifetime. And again, we've seen a lot of comets fail. And we saw one, we've seen a couple run into Jupiter. So
Hey, Drew?
yes.
Just as a side comment, with Halley's Comet, when it was coming back, they actually looked into historical documents and went back 26 orbits. And the orbit is about 75 years, so quite a ways back.
Yeah, and it's that's part of doing astronomical history, is trying to figure out what people were recording like 700 or 1200 or 1500 years ago when they say they saw things in the sky. But again, you could calculate how many more times it can come around. Each time is a little different, though, too. People who saw Halley's Comet in 1986, yeah, I was going to say it was the mid-80s, were not as impressed as people who had seen it 72 years before that, when we came quite close to it in our orbit when it was coming around the sun. This time we didn't, and it was a disappointing little smudge to people who were expecting something that would fill the whole sky. But it also didn't come in quite the same relation to the sun, so it probably didn't outgas as much as it had in that previous trip.
Well, we were on the other side of the sun when it was at its maximum.
Right, and as opposed to the apparition before that, when we were on the same side of the sun, and it made a bigger difference. And there was less light pollution than 76 years before that, too.
And we actually passed through its tail in 1910.
Right, and we had to wear our cyanide mask or whatever it was they were worried about.
Yeah,
yeah, that was a mistake. Anyway, so again, talking about the meteor shower, there are little meteor showers, there are big meteor showers, there are ones that last a long time, there are ones that last a few hours. The Perseids that peak in August, probably the shower that people are most aware of, Perseids usually in the end of May, and then they go on for more than a month after the August peak too. So it's spread out over a long time. And again, there are other showers that are recognized that last a matter of hours. So that has to do with how much junk there is in the particular comet's orbit, and how wide that orbit has become over how many ever times the comet has gone around the sun in it, and how we pass through that orbit. Again, thinking of it as a three-dimensional thing, we could go straight through the middle of the heaviest part of that kind of subway tunnel of stuff, or we could just graze the edge of it. So there's a lot of different meteor showers. There's also, comets leave behind different sorts of stuff too, which I'll get into in a minute. And the debris distribution is not necessarily uniform. This picture, this is Photoshop or whatever, making a nice even scattering of bits. In reality, that comet losing material happens in fits and starts. We see comets burst off material and then go somewhat more stable and burst off more material. So the junk in an orbit like this can be very clumpy. There can be a lot here and hardly any here. So if we hit a part of the orbit where there's a larger mass of stuff going by, we'll see more meteors. If we hit an emptier zone, we'll see fewer. So we end up with a calendar for the year, and it really doesn't matter what year you put up here, because the dates are about the same for each of these major showers. And each year at this span of dates, what we've got here is them saying two ranges. It's like when we'll first start recording meteors from this shower, this first one of the year, the quadrantids, in the end of December on the 28th, and they'll go through the 12th, and the peak is around the 3rd or the 4th. Same thing for any of these. Some of them, the peaks are, in this case, they're listing the one night that they're best actually for that year. And then we've got the comets that they're associated with along the side here. For instance, Halley's Comet is associated with the Aquarius shower. That's when we are passing through the orbit of Halley's Comet. Observing meteors. I just want to touch on this really quickly because this is a dark sky thing, and it's something I like to do. So if you want to go out and see meteors, the time of night makes a difference. Again, here we're back to Earth in its orbit going around the sun. Well, this is we're looking at the North Pole. I guess we could be looking at the South Pole, but to orbit this direction, it's the North Pole. So we're looking at the North Pole of the Earth here. This is where you're standing when the sun is setting, and now it's midnight, and then it's sunrise, and then it's noon as the Earth is turning around. I will see if I can add that in. There we go. So this is your time of day locally where you're on Earth. Well, this is where the Earth is heading, this direction. This is Earth's windshield right here. This is Earth's back window here. And you're driving along, you smatter into a lot more stuff on your windshield than you do on your back window. So we tend to see more meteors after midnight when we're coming around to the windshield side of the planet than we do after sunset. That doesn't mean we don't see meteors in this time. They can be in their own orbit, and they might be heading this direction from the lower right corner here up this way. And so they have their own speed, and they can catch up to Earth and still make a shooting star for us. But you'll see more after midnight. So, I wanted to point out too, we see meteors that aren't parts of showers. So go back to the when I was first showing you how much dust and debris there is just scattered around the solar system. We're always plowing into that stuff. So we can see what are called sporadic meteors, which means that they don't belong to any given shower. They're not in a comet's orbit, in other words. They're just junk that's floating out there, and they can happen at any time. Again, you'll see more after midnight and in the pre-dawn hours than you will before midnight, maybe 2 to 3 times more per hour in the before morning twilight than in after evening twilight. And for some reason or another, they also tend to peak in the autumn more than they and go through sort of a nadir in the springtime, which apparently just has to do with the distribution of that dust and debris around our solar system. So this is the time of year to be just out randomly seeing shooting stars that don't necessarily belong to a meteor shower. Here we are with a list of many of the recognized meteor showers from the year. You don't have to read all this, but what I wanted to point out, on meteor shower list, there's almost always going to be this thing called ZHR, which stands for zenithal hourly rate, which means the number of meteors you see an hour. Well, it means something. People take it to mean it's going to mean how many meteors you see in an hour. Let's look again. Let's start here at the quadrantids. It's the first shower of the year, and peaking in very early January, the first week of January. It's got this ZHR that says 120 on it here. And you know what? If this gets into the paper or on the news, or if somebody in media somewhere or another talks about this shower, they're going to say there's going to be 120 meteors an hour. Well, there won't be. Here's a table that's much more realistic and helpful. It's got 4 columns in it here. So we see that 120 number here, which is the calculated zenith hourly rate. And that is derived from a number of different things, and it really has nothing to do with how many meteors you're going to see in an hour. The 3 columns before it are much more practical. Here we have column 3 being you're in a rural sky, at least as dark as Flagstaff. It should be and moonless, and it should add here in all of these cases, you're able to see the entire sky from horizon to horizon, 360 degrees around. There's nothing blocking your view, and somehow or another your eyes are taking all that in. Or you have more than one observer, which is the better way to actually record and study meteor showers, is to have a few people who are each looking at their own quadrant of the sky, perhaps, and recording what they see there. So you might see 25 an hour more realistically there. If you're in a suburban sky or there's a quarter moon up, you're only going to see 10 an hour, probably at best, if you're lucky. And if you're in a city sky or there's a full moon up wherever you are, because it's like sitting under a streetlight, you're going to see 5 an hour if you're lucky. So this is a reality table of how things really work, as opposed to the ZHR, which is, I mean, I'm so tired of people saying Perseid meteor shower, there's going to be 100 an hour. That really misleads people. I've sat out under, say, suburban sky for a half an hour in the Perseid shower and not seeing a single meteor. And then maybe you'll see a couple within 5 minutes of each other and then not see any more for a while. So that number is, it's like selling bad telescopes that don't really work, department store telescopes that just frustrate people. This frustrates people when they expect to see more than one a minute and they don't. But I'm not saying don't go out and watch meteor showers. Just don't set your expectations unrealistically. Continuing on, observing meteors. There's that moon. So the shower happens at the same time every year, whichever given shower you're looking at. Some years, your favorite shower is going to happen when there's a big bright moon in the sky, and that's really going to hamper your ability to see things. So the moon is not your friend when you want to go meteor observing. You can see meteors wherever you are, depending your sky brightness, but there's a couple of things you should do to optimize your ability to see more of them. One would be wherever you are. My people are always like, which direction should I look? There isn't a given direction. When the people talk about, say, the Perseid meteor shower, yes, that's associated with the constellation of Perseus, but Perseus doesn't really determine where you might see a meteor in the sky. You can see a Perseid meteor shower in any portion of the sky over your head. I always advise people to look at the darkest part of the sky from wherever they're sitting. And also, again, not at the tree, but out at the sky. That kind of only makes sense. This is the biggest thing that you can do locally, is just not have any local lights shining around you or in your face, because that will always, no matter where you are, keep your eyes from being able to adapt to see the stars and the meteors. So even if you're in suburbia or something, just get it to a place in the yard where there aren't any lights that you directly shine in your eyes, or at a park. Or I've been in many places where I'm like, I just need to sit on this side of the car or something, so that light across the way isn't in my field of vision, so it's not disturbing my view. Equipment. This is the simplest kind of stargazing to do. The really only equipment you need is something to lie back on that lets you stare straight up at the sky without getting a crick in your neck. So a blanket on the ground, or an air mattress, or a wonderful reclining chair like this that goes all the way back flat. That's really what you need. If you want to be comfortable, you might want to keep yourself warm. Even in the summertime, even in August for the Perseids, I have ended up nights when got down into the upper 40s at night, and I was happy to have a sleeping bag or something to put in a chair like this and be comfortable. Something warm to drink is nice. A really expensive big telescope is what you absolutely don't want at all. You do not want to have a telescope when you go meteor observing, because as soon as you turn your head to look down in the eyepiece of the telescope, everybody around you is going to go, ooh, because they saw the meteor that you missed, because you're looking down at the ground and through a little telescope eyepiece when you should be leaning back, looking at the whole sky. So don't bring your telescope with you when you go to meteor observe. You might want to have something to make notes on. If you're interested in recording how many you saw or what part of the sky you saw them in, or how bright they were, like a digital recorder or a notepad. I think having a sky map, like a planisphere like this, is nice. If you're going to be lying back looking at the stars, you might as well bone up on your constellations, and gives you something to think about while you're waiting for a meteor to come around. But you really don't need to spend any money to go out and meteor watch. There, I'm up to part 3. Any questions else about meteors and meteor showers or meteor observing before I swing into meteor lab work? If not, I will plow forward. So part 3, meteorites. Again, reviewing, there's a lot of junk going around our solar system. And so the stuff I talked about that we run into that can potentially become meteorites, some of this debris that's just left over from the formation of our solar system, or all of this asteroid stuff. These asteroids occasionally bash into each other, or occasionally a planet like Jupiter disturbs one of their orbits and drops it in to fall toward the sun and potentially get run into by Earth. Or they run into each other and break up and shatter pieces going out in all sorts of directions. And then there's comets, which actually are not a source of meteorites. The solids, the non-volatile solids that are in comets are small. There's no meteorites that have been shown to be related to cometary origin. So, which kind of makes sense from our understanding of comets. Again, they're more like a Swiffer that's full of dust and things from the solar system. They're not a place where these minerals would be aggregating together and forming large enough bodies to make it to Earth as a meteorite. Go ahead here. Okay, so as a side shoot here, just to stop and think for a minute about studying things like the formation of a solar system, of a planetary system around a protostar. How can we study things that are far away in space and or far away in time? This is what makes astronomy really different from a lot of the other sciences we think of. When you think of a scientist, you're often thinking of somebody who is doing something in a laboratory, who's taking something apart or investigating somehow or another how something works. You can get your hands on it and do something with it. Well, we don't. Oh, you like that one down there? We don't have an enterprise that we can go out and visit a protostar with a solar system forming around it, or to be able to go back in time and see our sun and planetary system forming. But this is the interesting thing that we can do via meteorite studies. There are these materials that have their origins and their dates back from that time of the formation of our solar system and around and thereabouts, and they're still out there, and we occasionally run into them and they fall to Earth, and we can pick them up. We can take those into our labs and do investigation with them. So meteorites are samples from other places and other times, and I'm not going to ask you to even absorb all of this. This is a table with dates on it. So we're going to look at the x-axis here, I'm sorry, the y-axis here, we've got dates in millions of years ago. So basically, we're looking at a range of time at around 4.5 billion years ago. And what we've got here is studying of different things in meteorites. So we're looking at different actual meteorites and different formations with them, different materials than the CAI is a calcium aluminum inclusion. And they were the first things to start condensing into solid particles around the protostar in this the disk formation of our solar system. We end up with dates on these that are amazingly accurate. We're looking at things 4.5 billion years ago that are being dated to in less than 1 million years. So it's like saying, I not only know that, you know, there's a bird flying around in New York from here, I know from here that that bird is within a few inches of this certain point. This is what we're doing looking back in time this way. All of this data has led to this line being drawn here, which is officially now accepted as the age of the starting age of the official birth date of our solar system, which is 4.567 billion years ago. All of these dates don't come from looking at other stars or looking at the planets in our solar system. They come from looking at meteorites in the laboratory. And this down here is the little key to it. You need to do that. Oops, no, I went backwards somehow. These are all isotope measurements. So those of you who know your chemistry can see which isotope progressions we're looking at here to make these measurements of these ages from meteorites. So this is us studying the formation of our planetary system, our sun, that happened over 4.5 billion years ago by looking at space rocks. There's a lot of different kinds of space rocks. They're not all from the same place or the same time. I could go into this for, forever. You could have a course in this, but really quickly, there's two different groups here with all sorts of subgroups underneath them. The first is, there we go. So what is an undifferentiated meteorite? Well, this is the stuff that I, in my very uneducated way, refer to as the sawdust left over from the building of our solar system. This is the stuff on the shop floor, basically. So it's directly the material that was condensing and aggregating out of this cloud where the planets formed, and it's leftover stuff like that. That's pretty much, it can be fairly pristine from that time, that 4.5 billion years ago. The differentiated meteorites are dating to that era, but how they got differentiated was that material had to condense into a body that was big enough to become molten and have gravity sorted out. In other words, you've got a body that's molten and the metal is sinking to the core because it's denser, and the stone is floating to the top because it's less dense. And so this process has taken that stuff from that nebula and altered it. That's what the differentiation means. So the way you get iron out of a cloud of stuff condensing around the sun that's less than 1%, if you're going to count the atoms wise, iron, way you can get fairly purified iron is to form a body where the iron sinks to the core of it because the iron is the densest thing around. So you're going to have bodies like this forming in the proto-solar system. How do we get the iron out of it? Well, what that means is something nasty happened to one or more of these bodies, because we've got stuff from its core being strewn out across space to become asteroids and meteorites that fall to Earth. So something nasty happened to one or more of these differentiating bodies to make these meteorites eventually available to us on Earth. Looking at them more again in person here, let's click this way. Stony meteorites are basically that. They're stone. There's fewer kinds of minerals out in meteorites than there are on Earth by far. The rock on Earth has been altered by a lot of things that there aren't out in space. It's been altered by the large presence of water, of liquid water. It's been altered by oxygen and other things in our atmosphere. It's been altered by even by biological activity. And so there's a small family of different minerals that we find in meteorites. Most of those minerals are found on Earth also. We can get into the irons, which again are the core of something. We cut open an iron meteorite and polish it and etch it. We see the crystals in it, which form when this molten body cooled very slowly. These crystals take thousands or tens of thousands of years to form as the temperature is dropping by like a degree a century. It's incredibly slow cooling it takes to grow crystals like this. But we have them there, and they're quite pure metal, iron and nickel. And then we have the stony irons, which look similar to the irons, but when we cut them open, we see that they are a matrix of the nickel iron with mineral crystals embedded in it. To break down a little bit more importantly here, we're going to try to make our slide go forward. The stony meteorites really importantly go into two classes. We have the chondrites and the achondrites. And pretty much the division here is the achondrites go with the iron and the stony irons to be from differentiated bodies. The chondrites tend to be the material from that proto-nebula, to the very primitive stuff. The chondrules are little round balls of mineral inside of these. That's where they get the name chondrite, because they have the chondrules. Those chondrules are things that actually formed out there in space in that nebula as it was condensing. And so it's a process of condensation. So these are extremely primitive things from the very dawn of our solar system. If we look at how common these things are in actual falls of what comes to Earth, 86% of the meteorites that fall to Earth in this era where we live today, in this era that we live in, is chondritic stony material. So it's that leftover stuff. Only 5% is iron, 8% are achondrites, and actually a little less than 1% are the stony irons. So this is that differentiated material. There's less of that falling to Earth now than there is of this leftover sawdust material. Other things that fall to Earth, this is a piece of Mars, actually. I was polishing that, I don't know, a month or two ago. We did a section of this, and then I polished it to make it look pretty. So this is a brecciated impact breccia from Mars. How you get a rock off of Mars is you hit it with an asteroid hard enough to make a crater with enough energy to blow some of the ejecta of that crater away from Mars's gravitational hold and out into space. And again, it can circle the sun for millions of years before Earth happens to run into it, or less. It can be kind of a random amount of time it takes. It's chaos pretty much for when we're going to run into something.
Is that a sugar type?
Yes. I'm trying to think of its official classification. This is the one known as Black Beauty. It comes from the Sahara Desert, as many meteorites do. So, yeah, this piece here is a piece of our moon. Same thing. Something hit our moon hard enough to blast away some ejecta from the crater with enough force to have it leave the moon's gravitational hold, and some of it then subsequently fell to Earth. And so we have quite a bit of moon rock. I'm not sure. I need to look up now whether we've got more massive moon rock from meteorites or from the Apollo missions. I think meteorites are probably ahead because there's a number of lunar meteorites and some of them are fairly good size. Anyway, so not everything that falls to Earth as a meteorite is from the asteroid belt or beyond. We do have these planetary things too. Somebody was hypothesizing that they had a meteorite from Mercury, but nobody else believed it because it's really extremely hard to figure out the mechanics of how you would get something to push farther out in the solar system from a body, like if something impacted Mercury, to make it all the way out to Earth. It's very easy to figure out how something from Mars would fall in toward the sun. But anyway,
we have stuff in the moon and Vesta as well.
Oh yes, we have quite a few meteorites that are related to Vesta. So Vesta, but again, Vesta's out in the asteroid belt, so things could fall in from there. And the way we know that is we look at the spectra of the asteroid Vesta, and we can see its spectra clearly enough to see quite definitely the ratios of various minerals on it. And then when we find a piece of rock that looks just like that, a meteorite that looks just like that, there's a whole class of them actually that share that spectral look. So they're considered to be related to Vesta. So.
There's also, earlier this year, they're still looking at the Apollo material they brought back, and they found a piece of Earth.
Yes, that
was
is true.
On the moon.
Yeah, one of our grad students was working on Apollo material. It's still very much heavily being researched. So this is in the lab. Actually, look, and again, this is how we get our hands on these things from long ago and far away. We take apart meteorites in all sorts of different ways. This up here in the corner is freeze thawing to shatter the minerals apart. We put in liquid nitrogen and put in hot water, and liquid nitrogen, hot water, and the tube that it's in, that is, and use freeze thawing to shatter it apart. My boss Jim here is using, we use acids to remove harder minerals from the softer minerals in stony meteorites. I've spent a lot of time picking out crystals of specific minerals that we're looking to study from pulverized meteorite material. This is using scanning electron microscope with there's a way to use an electron beam to do a elemental analysis. So here you're looking at the screen. This image is probably this is a mineral crystal here. It's probably 50 or 60 microns across, I'm guessing, looking at it. We hit it with an electron beam, and the wonderful machine on the side of the SEM here gives us this wonderful elemental breakdown of what is at each spot in here. So we're looking at how these crystals form, how they vary across them, how they compare to Earth forms of the same mineral. So again, this is taking space and being able to bring it into the lab and take it apart and do measurements on it, like those other scientists get to do with their stuff. So, what can we measure? This is only a partial list, really. Elemental abundances, isotope ratios, the physical compositions tell us a lot about how these things formed, what the conditions were when they formed. The physical history tells us about how they were altered. Things get altered by, let's see if I put it here. I think I put it here. Yeah, there we go. They get altered by their exposure to heat and cold and pressure and shock and radiation. There's a lot of radiation out in space. We can tell how long that rock took to get to Earth from Mars by seeing how long it was exposed to cosmic rays out in space. So these are all lab-based things that we can do. We can look at chemical reactions, and there is a lot of water in space. One of the ways we look at the we classify stony meteorites is by how much they've been altered by water, and not on Earth, but out in space. So there is water out in space. Well, think of all those comets. They're made of frozen water. So again, this is how we get these interesting questions answered about our solar system in general by looking at these things in the lab and using it to decipher what was going on billions of years ago. And there, I've reached the end.